What is going on, everybody, and welcome to part 7 of the Deep Learning with Python, TensorFlow, and Keras tutorial series. In this part, what we're going to be talking about is the recurrent neural network. So the idea of a recurrent neural network is that the order of some data carries significance and importance. So two areas where this tends to be the case is in like time series data, where data is organized temporally or chronologically. Otherwise, you might have, this is important in natural language, so the order of something in a sentence carries a lot of importance as far as the meaning of that sentence. So, for example, if you said, some people made a neural network, what happens when you feed it through some sort of natural language processing algorithm, let's say that was just a deep neural network, what usually tends to be the case is we're going to tokenize data, which just means, let's say in this case, we're going to split it by word. So each word is its own unique feature. But the problem with a deep neural network is this sentence would have the same meaning as a neural network made some people. And obviously, these two sentences have widely varying meanings and impacts and all that. So it's important, the order of things in these sentences. So that's the idea of a recurrent neural network. So how do they actually work? And I've got some beautiful, beautiful drawings. I don't know who drew those, but man, they're beautiful. Anyways, so the idea here is that, let's say these green boxes here, these are recurrent cells. So you could have a basic recurrent cell. Very rarely do these get used. Usually it's like an LSTM, which is short for long short-term memory. There's also the GRU, or gated recurrent unit, but again, I just pretty much see everybody use LSTM cells in all honesty. So the way these work is, you've got your sequential data here, and the sequential data is passed in, let's say, to one of these cells, and then the cell does it outputs to two locations. It outputs one to the next layer, but two, and the next layer could be the next, it could be input to the next recurrent type of layer, or it could be the output layer or a dense layer, who knows. But anyways, each cell is going to output somewhere to another layer, but also down to the next node in the specific recurrent layer. Now, where these output to, it doesn't necessarily have to be to the next thing down, and then it also doesn't have to only go in one direction. You could have bidirectional recurrent layers, for example, and you can get really crazy with the order of things and where data gets passed and stuff. But in general, this is a super basic one. So another way to look at it is like this is one cell, and so let's say you've got basically, let's say this is like the second one in the layer. So let's say it's like we're looking at this cell right here. So this green box is this cell here. Okay, so basically some data has come from the previous cell. It's wrapped around here. It's coming in, and the LSTM cell that we're looking at here, it chooses, okay, what do we want to forget from the previous node? Then there's input data coming in. Okay, based on this input data, what do we want to add to this bundle of info that we've got? And then finally, okay, based on this bundle of info, what do we want to output to both the next layer and the next node that we want to output to? So that's the task of the LSTM cell. Now, obviously that's pretty complicated, especially when, all these things, like the whole point is to eventually just pass along like a scalar value. So how do we do that? Very challenging stuff. If you want to learn more about how LSTM cells work specifically, there is a great timeless write-up on the LSTM cell. I linked to it in the text-based version of the tutorial, so definitely go check that out if you want to. Otherwise, let's get into writing our own basic recurrent neural network. So what we're going to do in this video is just do a really simple one, just so we can get the idea of like how easy a recurrent neural network itself is. But the hard part with recurrent neural networks is getting your data set structured in such a way, because the type of data that you're going to be using typically doesn't have targets. It's just time series. It's just informal kind of data, and we don't really have, what are we actually trying to point this to? So there's usually a huge amount of pre-processing involved in when you work with recurrent neural networks. So what we're going to do here is just use a simple MNIST example, and in the next tutorial we'll do a realistic example with some time series data, specifically with cryptocurrency prices. So yeah. Anyway, I'm going to minimize this, and let's begin with some imports. So import TensorFlow as jerk. Always does this to me. Import TensorFlow as TF, fix that. Then we're going to go from TensorFlow.Keras.models. We're going to import the sequential type of model. From TensorFlow.Keras.layers, we're going to import the dense layer, one because the output layer itself needs to be a dense layer, but also we are going to end with another, like a realistic, a dense layer before the output layer. That's a pretty common operation to do. Then we're going to have some dropout, just so nothing gets overly weighted, and the LSTM cell. I am going to comment here, if you are on the GPU version of TensorFlow, check out the cuDNN LSTM cell. So even if you are on the GPU version of TensorFlow, this LSTM cell will indeed run on your GPU, but the cuDNN LSTM cell is even more optimized, and it's like 5+ times faster, even though both run on your GPU. If you're on the CPU version of TensorFlow, well, then you're gonna. This tutorial, this model is gonna take like 5 hours to train or something. Either way, okay. So those are the things that we need, and now we need the data set. So we're just going to grab MNIST real quick. So MNIST is equal to tf.keras.datasets.mnist, and then we just need to unpack it. So it's just these two tuples, and then it's x train, y train, then it's x test, y test, and that's MNIST.load_data. So again, my apologies for using MNIST, but I think it's better to make this one as basic as possible, and then in the next one we'll get in, because honestly, it would take us, the next one's probably going to take us 2, 3, maybe even 4 parts just to get to, okay, now feed it through the neural network. And that's the easy part, really. Feeding it through is not too hard. So for example, let's just do a print xtrain.shape, and then we should be able to deduce this from the above, but xtrain, and let's just get the first sample dot shape, just so we get an idea what we're dealing with here. So so we can see we got 60,000 examples of 28 by 28 images, and of course the 0th element is just 28 by 28. So take a minute, pause, and think about, okay, so this is our training data, and it's already in sequences for us, right? And what are the sequences? Well, it's in sequences, like what is this 28 by 28? Well, it's 28 rows of 28 pixels per row. So we could, in theory, say each row is a part of a sequence. And if you were to take the first row and then kind of scan downwards, could you figure out what the number is? Probably. So the hope is that a recurrent neural network could actually do this, and maybe even more so, we should see that it could plausibly do it better than a deep neural network, but we'll see. The more important thing is just to show the recurrent net anyways. But yeah, so that's the sequence. It's a sequence of rows of pixels that we're going to be feeding through this neural network. So now we want to build the actual model itself. So we're going to say model equals, I'm going to give us some space here. Model equals, and it's just going to be that sequential type of model. Now we're going to do model.add, and we're going to add in an LSTM cell. How many, or LSTM layer, rather. How many cells do we want to have? We're just going to use 128 for now. We're going to specify the input shape, and that is 28 by 28. We already kind of know that. But we can make this somewhat dynamic by doing xtrain.shape, and then 1:. So then we can pass an activation function, and we'll use our good friend rectified linear. And again, do check out DNN LSTM. I'm just not going to do that yet. I'll probably change it before we run it because it is really, really fast. But for now, we'll just keep it. Whoops, didn't mean to move that. We'll just keep it here. Okay, so the next thing that we want to do is one more parameter, which is return underscore sequences, and that's going to be true. So do we want this layer to return sequences, like it was input, like sequences were input, or do we want this layer to return something flat, right? So if we're going to a dense layer, we wouldn't want to return sequences because a dense layer is not going to understand what the heck's going on. But if we're going to another recurrent layer, we definitely want to return those sequences. This is just a long line. Anyway, okay, so that's one of our layers, and then we're just going to do model.add, and we'll throw in a dropout because that's what you do. So we'll do a 20% dropout there, and then we'll do another layer. So model.add, we'll add an LSTM layer. We'll do another 128. We don't need to specify input shape. In fact, I don't know why we ever had to. And then we'll pass an activation function here. Activation equals rectified linear. We'll do a dropout. I'm just going to copy and paste. Copy, paste. And then let's do a model.add. We'll add a dense layer. We'll make it 32 nodes. And then activation. Gosh, can you guys think of what activation? Oh, yes, that's right. Rectified linear. And then we'll do a dropout. And then we'll go to the final dense layer. So I'm just going to copy this, paste, and I'm just going to hard code in 10. It's just how many classes do you have? So we're just going to go with 10. The activation shouldn't be rectified linear. It should be softmax at this point. And okay, I think we're done there with at least with our model structure. Now all we need to do is do the compile and then the fitment. So to do the compile, we're going to have an optimizer compile. Anyways, tf.keras.optimizers.atom, and we'll just specify a learning rate of 1e -3. And then we'll do a decay. Well, we haven't really talked about decay, but we'll do a decay. 1e -6 or something. Probably that's too small. Maybe 1e -5. So a decay is just over time. We'd probably you want to start with a larger learning rate to take those large steps that you want to take, and then but over time you'll kind of find this local spot. But probably if you took smaller steps, you could do even better. So if you keep taking those big steps, you're going to keep bouncing around that little U shape. But if you take a smaller step, you could plausibly do better. So anyways, that's what decay is about. It's just over time, every batch, it's going to decay the learning rate a little bit. So it's going to keep shrinking that learning rate. And so you'll take smaller steps. Anyways, model.compile, and we'll say loss equals sparse categorical cross entropy. I just want to say they did add a shorthand for mean squared error. Squared error. That's one way you can measure loss, and they said it's now you could use MSE. I'd really like it if they added shorthand for all of them. Someone tell me below if they have, and I just don't know about it. But I'd like to be able to just say SCC. That'd be nice. I hate typing that out. Okay, so we got our loss. The optimizer equals opt. Really simple there. And then the metrics that we're going to track here, we'll just go with accuracy. And then finally, model.fit, xtrain, ytrain, epochs. We'll do 3 epochs. Validation data, so we can see it over time, will be xtest, ytest. Okay, so that should be good to go. Hopefully I can run this and not crash the computer, because I know Sublime likes to really get me. So we'll go ahead and run that now. I'll probably just go through maybe one epoch. Oh, let's see. Invalid syntax at the dropout. What did we, and maybe not, what line is that? 14. Did we not fully close this off? We didn't. Try again. Wait for it. Okay, things are looking good so far. All right, and we are off. We are learning. The accuracy does not look very good. But you can see how slow this is. Like, this is extremely slow. I would expect accuracy to be a little better even by now. I wonder why this is going so painfully slow. I wonder if I've made a mistake even. Because I don't even see loss going down. It almost looks like loss is going up. 143938. No? First I saw this, I was like, oh, that's our problem. No, we've got our final dense layer. Activation is softmax. What did we screw up? We have to have screwed up something. It should be learning much more by now. So this isn't it. Oh! I don't know that we've ever showed this, but I brought it up at least. What aren't we doing here? We are not normalizing this data. So we could use the Keras normalization, or we can just say xtrain equals xtrain divided by 255, xtest equals xtest divided by 255. I'm going to save that. The other thing I'm going to do while I have you guys is show you cuDNN LSTM. So let's go ahead and import that as well. I'm going to change this to cuDNN LSTM in this one. And then you can't, the cuDNN LSTM uses a tanh activation function, which is, you can Google it if you want to see like the shape of it. But you should be able to, with rectified linear, you should still be able to get a good accuracy here. But the problem was I almost kind of want to show you guys, because I know some people aren't going to be able to run this if they're on CPU and they just want to learn. So I guess I'll just rerun it. But we can even see, so like this did not train, and hopefully that was the problem. I'm going to be really sad if that's not the problem. But almost certainly the reason this didn't train is because we didn't scale between 0 and 1. So let's see the example. Yeah, I mean, look how much faster it's learning now. All we did was scale it between 0 and 1. That's how huge of an impact that makes. So yeah, it's super important. Okay, so I'm going to go ahead and break, well, I guess I don't have to break it, but I'm going to show you guys now cuDNN LSTM because it's so fast. Anyways, paste, and then I'm going to delete this and delete this. Whoops, we do want to have that though. So see, we're already at like 41, 40. I'm sure we're going to get into like the 90s or something. But let me ETA to 3 minutes. So now let's run this one. Hopefully I'm not going to crash the GPU. Sublime's pretty bad. I probably should be running this in a console instead, but whatever. Look at this. Look how fast this is. This is the best thing ever. What a great little addition. I mean, recurrent nets are so slow. This cuDNN LSTM cell is just glorious. So we're already at an accuracy of 96%. And before epochs were taking, I don't know, we were pretty deep into that one, and it was like 2 minutes and 30 seconds to go. Whereas these entire epochs are taking 13 seconds. That's crazy. Okay. So I think we're only going to run for 3 epochs, so I guess I'll just let this one finish. Good, done. So validation, so accuracy here, 97.73. Validation actually did better, 98.11. I don't know if I can get back to the other layers or not. I did want to show, like on this, so like on something like this, I think the reason why validation accuracy is higher than accuracy is because this is an average for the entire epoch, whereas this is like at the end of the epoch we run it. So, and that's also why like this is an average for the epoch. So then after the next epoch, we can see a lot of times our average will jump quite a bit. But even in this case, it's still lower than the validation accuracy, which tells me we actually probably could have continued to train because by the end of the epoch, we were much, much better. But we could also look at it in TensorBoard as loss still falling and all that. So anyways, that is all for now. In the next tutorial, we will go over a far more complex example of doing this on like a realistic time series data set, because it just takes so much more work. But I didn't want to bog us down with the pre-processing without this, because actually, feeding it through a recurrent net itself, as long as you have data that's already in sequential form and already has a target, it's actually pretty simple. So anyways, that's it for now. A quick shout out to the most recent channel members, Taj, Jagdish, Dana Larson, and Juliano. Sorry if I mispronounced anybody's names here. It's pretty crazy how many people's different names that I've never heard before and I have no idea how to pronounce, so I'm really sorry. But it's just crazy, my audience just comes from everywhere, so it's really cool to see, and again, thank you guys so much for your support. It's really appreciated. So anyway, that's all for now. If you have questions, comments, concerns, whatever, feel free to leave them below. If I did screw something up in general, it is a red flag if validation accuracy is higher than accuracy. But I do believe my explanation before is why that's the case. Also, I'm very confident that their data is prepared correctly. But anyways, if that ever does happen to you, that should always be a massive red flag. Keep training and make sure that is not the case forever. Anyways, that's it for now. Questions, comments, concerns, whatever, feel free to leave them below. If you've got any requests for things that you'd like to see in this series, let me know. Otherwise, I will see you guys in another video.